Yesterday, a magnitude 6.0 earthquake ruptured the seafloor off the southern coast of New Zealand, and it landed on the exact same plate boundary that, weeks ago, produced the largest earthquake on Earth this year. New Zealand is now sitting in the middle of a fault line that has lit up at both ends in a single week. So is this the warning shot for the magnitude 8 the country has been overdue for? In the next few minutes, I'll show you what the data actually says, and where New Zealand's real danger is hiding. Let's get into it. Yesterday, a magnitude 6.0 earthquake ruptured the seafloor off the southern coast of New Zealand. It struck just before 1 o'clock in the afternoon local time, in the stretch of ocean between the South Island and the subantarctic Auckland Islands, roughly 460 kilometers, about 286 miles southwest of Invercargill. The United States Geological Survey catalogs it as a reviewed solution, which means a human seismologist has already checked the automated result. The numbers are these: magnitude 6.0 at a shallow depth of about 14 kilometers, a little under 9 miles down. There was no tsunami. The USGS issued a green alert, meaning little to no expected damage. And because the epicenter is remote, almost nobody was there to feel it. So if nobody felt it and nothing broke, why does this earthquake matter? It matters because of where it landed. This quake did not strike empty ocean. It landed directly on top of a dense band of hundreds of past earthquakes, a band that marks one of the most active and most unusual plate boundaries on the entire planet, the boundary that New Zealand is built on. And in the span of a single week, that boundary has lit up at both ends, with New Zealand sitting right in the middle. So the real question is not whether this one magnitude 6 did any damage. It didn't. The question is whether it is a warning shot for the earthquake New Zealand has been dreading for 300 years. Let's get into the data, and I'll show you exactly what it says. Everything here comes down to two giants grinding against each other, the Australian plate and the Pacific plate, colliding at several centimeters a year. That collision line is the red boundary you see slicing across any earthquake map of this region, and New Zealand is built directly on top of it. But here's the part that makes New Zealand one of the strangest tectonic settings on Earth. The boundary does not behave the same way along its length. It actually flips polarity as it passes through the country. Follow it from the north. North of New Zealand, you have the Hikurangi Margin, then the Kermadec Trench, and then the Tonga Trench. Along that northern stretch, the Pacific Plate dives westward, down and under the Australian Plate. That is a subduction zone, and the northern end of it, up by Tonga, is the fastest plate convergence measured anywhere on the planet, up to around 24 centimeters a year. That is nearly 10 inches every single year. That speed is exactly why Tonga gets hammered, again and again, with enormous subduction earthquakes and explosive undersea volcanism. Now follow that same red line south, straight through New Zealand, and something remarkable happens. South of the South Island, the polarity reverses. Along the Pusagur Trench and the Macquarie Ridge, it is the Australian plate that gets forced down and sideways, beneath the Pacific plate, the opposite of what is happening up north. And this is where yesterday's magnitude 6 struck. So the southern end and the northern end of this boundary are mirror images of each other, two subduction zones pointing in opposite directions, connected straight through the middle of the South Island by one of the most famous faults on Earth. Think about how unusual that arrangement actually is. Most plate boundaries do one thing along their entire length. They pull apart, or they slide past each other, or one plate dives under another in a single, consistent direction. New Zealand sits on a boundary that does all of these things at once, switching from subduction in one direction to a sideways grinding transform fault, to subduction in the opposite direction, all within a few hundred kilometers. The entire country is essentially balanced on the seam, where two tectonic plates change their minds about how to collide. That is why New Zealand has earthquakes, active volcanoes, geothermal fields, and rising mountains all packed into two narrow islands. It is one of the most geologically active pieces of land on Earth, and it is not by accident. We will come back to that fault, because it is the one that should actually worry you. But first, I want to show you what yesterday's earthquake actually did, because there is a detail in the data most reports skipped right over. When seismologists want to know how a fault moved, They look at something called the moment tensor, the little beach ball diagram you see on earthquake reports. That diagram is not decoration. It tells you the mechanism, the actual motion of the rock. And yesterday's beach ball is clean. It shows compression, one block of crust being shoved up and over another, what we call reverse, or thrust, faulting, possibly with a sideways oblique component. In plain English, the ground was being squeezed, and something gave. Why does that matter? Because it fits the tectonics of this exact spot perfectly. South of New Zealand, the Australian and Pacific plates are converging at an angle, squeezing the crust, and a thrust earthquake is precisely what the textbook predicts there. This was a textbook event. Just as importantly, it tells us what this was not. This was not a volcanic signature. If magma were moving underground, the data would look completely different. You would see earthquake swarms, low-frequency events, strange mechanisms that do not fit a simple fault. None of that is here. This beach ball is plain, clean, tectonic, and in the best possible way, boring. The depth tells the same story. At about 14 kilometers, this was a shallow rupture in the upper crust brittle rock snapping near the plate boundary zone. It was not one of those events from hundreds of kilometers down that we will talk about in a minute. And that shallow depth is a double-edged detail. Shallow quakes shake harder and produce more aftershocks. But out where this one hit, there is almost nobody to shake. So on its own, this is a routine, well-behaved earthquake in a remote place. It is worth pausing on that word, shallow, because in earthquakes, depth changes everything. An earthquake 15 kilometers down delivers its energy almost directly to the surface above it, which is why shallow quakes do the most damage when they strike under populated land. The same magnitude 200 kilometers down arrives at the surface weakened, spread out, and softened. Yesterday's quake was the shallow, hard-hitting kind, but it struck under open ocean with no one above it, so the energy went into the water and the empty seafloor rather than into homes and infrastructure. Move that exact rupture a few hundred kilometers north, under the South Island, and we would be having a very different conversation this morning. The reason it is worth a closer look is the neighborhood it happened in, because this particular stretch of fault has a serious history. The Puisagur and Macquarie segment, where yesterday's quake struck, is one of the most seismically active plate boundary segments in the entire southern hemisphere, and its record proves it. In 1989, the Macquarie segment produced a magnitude 8.2, one of the largest strike-slip earthquakes ever recorded anywhere. In 2004, the Macquarie region fired off a magnitude 8.1 just days before the catastrophic Sumatra earthquake on Boxing Day. And in 2009, the Dusky Sound earthquake in Fiordland reached magnitude 7.8, struck right on the Puisagur subduction interface, became New Zealand's largest earthquake in nearly 80 years, and generated a small local tsunami. So set against that backdrop, a magnitude 6 here is completely normal behavior. This segment produces magnitude 5s and 6s routinely, magnitude 7s every decade or two, and it is capable of a magnitude 8. Yesterday's quake is not unusual. It is the neighborhood that is serious, not the event. There is a detail about this southern segment that most reports miss entirely, and it is genuinely fascinating. The Puisagur subduction zone is considered one of the youngest subduction zones on the entire planet. Geologists call it an incipient subduction zone, a trench still in the process of being born. The Australian plate only recently, in geological terms, began diving down here, and that raw, immature, off-angle collision is messy. It does not slide cleanly. It jams and grinds and snaps. And that is exactly why this young, awkward boundary produces big, oblique thrust earthquakes, like the 2009 Dusky Sound event. So when a magnitude 6 ruptures here with a thrust mechanism, it is not a surprise it is this young subduction zone doing precisely what a young subduction zone does. The crust is being shoved together faster than it can comfortably absorb, and every so often, a piece of it lets go. Yesterday, a piece of it let go. That raises the question everyone actually wants answered. Could this magnitude 6 be a foreshock, the small one that comes before the big one? Statistically, any earthquake can be a foreshock until proven otherwise. But the numbers are clear, and they are reassuring. Roughly 90 to 95% of magnitude 6 earthquakes turn out to be main shocks, the biggest event in their own sequence. You should expect some aftershocks out there now. in the magnitude 4 to 5 range. A jump up to a magnitude 7 or higher is possible, but it is statistically unlikely. And here is the thing, this remote offshore segment was never where New Zealand's real danger sits anyway. To understand the actual threat, I have to take you back to that fault running through the middle of the country, the one I promised we would return to. Connecting the two flip subduction zones, running straight up the spine of the South Island, is the Alpine Fault. It is not a subduction zone at all. It is a transform fault, a place where the two plates grind sideways past each other, and it is enormous. It runs about 600 kilometers, nearly 500 miles, as a single, sharp scar that you can clearly see from space. And the Alpine Fault is the reason this whole story matters, because it is overdue. The Alpine Fault ruptures in a roughly magnitude 8 earthquake about every 300 years. We know this from the geologic record, layer by layer. The last time it ruptured was the year 1717. That is more than 300 years ago. Do that math, and the fault is past its average. This is not vague hand-waving either. The scientists at New Zealand's GNS Science put the odds of the next major Alpine Fault rupture at around 75% within the next 50 years, with a strong chance that it is a large, magnitude 8 class event. Read that number again. Not 75% over the next 1,000 years, 75% within the next 50. That means it could be today, tomorrow, next year, in a decade, or in 40 years. But on the scale of a human lifetime, that is a genuinely high probability hanging over a fault that runs right through where people live. When the Alpine Fault does go, it will not be subtle. Each of the last several ruptures moved the ground sideways by roughly 8 meters in a matter of seconds. And a full rupture is expected to produce a magnitude around 8, with violent shaking lasting up to several minutes across the South Island. It would sever the few roads and power lines that cross the Southern Alps, isolate West Coast communities for weeks to months, and shake loose thousands of landslides. New Zealand's emergency planners do not treat this as a hypothetical. There is a national scale response plan, called AF8, built specifically around the near certainty that this fault will rupture within many people's lifetimes. That is how seriously the science takes it. When a country builds a disaster plan and names it after the fault itself, you know the threat is not theoretical. And the Alpine Fault is not even the only loaded gun. Off the east coast of the North Island sits the Hikurangi subduction zone, New Zealand's own miniature version of the Tonga Trench, capable of a magnitude 8+ megathrust earthquake and a serious tsunami that would threaten Wellington, Napier, and Gisborne. So when people ask whether New Zealand is in danger, the honest answer is layered. From yesterday's magnitude 6? No. But New Zealand lives on one of the most energetic plate boundaries on Earth, with an overdue Alpine Fault and a locked Hikurangi megathrust sitting under its most populated regions. That is the real threat. And it is exactly why a quake at the far southern end of the boundary makes seismologists turn and look, especially during a week when the opposite end of that same boundary is also on fire. While the southern end of this boundary was rupturing, the northern end, up by Tonga, has been anything but quiet. Back in March, on the 24th, a magnitude 7.5 earthquake struck near Tonga, the strongest earthquake recorded anywhere on Earth so far this year. Now, that one was very different from yesterday's. It happened far below the surface, around 238 kilometers down, and it was a normal faulting event inside the sinking Pacific slab, not a shallow megathrust. That depth is exactly why it did not produce a major tsunami, even though sirens sounded in the Tongan capital and a tsunami warning was briefly issued and then lifted. And that Tonga segment has not gone quiet since. Just days ago, on June 6th, it produced a magnitude 5.3 near the same region. The activity does not stop at the surface, either. This past week, a cluster of earthquakes fired in the Fiji region at extraordinary depths between 500 and nearly 600 kilometers down, 300 to 370 miles below the surface. Those are not surface faults. Those are earthquakes happening inside the Pacific slab itself, the slab that the Tonga Trench has dragged far down into the mantle, and the rock is cracking as it sinks. On June 9th, another one of these intermediate events struck south of the Kermadec Islands. About 388 kilometers down, the same sinking slab flexing again, this time closer to New Zealand. There was even a magnitude 5.4 near Vanuatu, on a neighboring segment to the west. To understand why this northern end is so violent, picture what is actually happening to that slab. As the Pacific plate is dragged down at the fastest convergence rate on Earth, it does not simply slide away and disappear. It bends, it stretches under its own weight, and it tears, and those stresses are released as earthquakes hundreds of kilometers below the surface, the very ones showing up under Fiji and Kermadec this week. The same system has a track record of major events. In 2021, a magnitude 8.1 struck near Raoul Island in the Kermadec chain, and the 2022 Tonga eruption, the most powerful volcanic explosion in over a century, which sent a pressure wave around the entire planet, sits on this same boundary. This is a place that produces some of the largest earthquakes and most violent eruptions found anywhere. When it rumbles for a week straight, that is just an ordinary Tuesday. So add it all up. In one single week, the Tonga end was active at the surface, and far below it, the slab beneath Fiji and Kermadec was creaking under the strain. A neighboring segment moved near Vanuatu, and then the southern Puisagur end ruptured at the surface with yesterday's magnitude 6. New Zealand is sitting in the middle of a plate boundary that has lit up at both ends at once, which leads to the question that is all over the internet right now. Are these earthquakes triggering each other? Is the whole boundary waking up? Here is the honest answer, and it is important. No, there is no physical mechanism that connects a far-down slab earthquake near Fiji to a shallow crustal rupture 3,000 kilometers to the south a few days later. Earthquakes can sometimes nudge each other, we call it dynamic triggering, but that generally takes a magnitude 7.5 or larger source, and it acts on nearby faults that are already right on the edge of failure, not across an entire ocean. The static stress changes from one quake to another are local. They do not reach across the length of a plate boundary. So why does the map look so coordinated? Because the whole boundary is permanently active. Remember that number from earlier, up to 24 centimeters a year of convergence at the northern end, the fastest on the planet. A boundary moving that fast does not take weeks off. A week with quakes at both ends is not a signal that something has woken up. It is the baseline. This is the machine that never stops. You will also see a popular claim online that recent research on faults, self-triggering faults, like the San Andreas and Cascadia setting themselves off, proves the whole boundary is dragging New Zealand toward its big 1. Self-triggering and cascading ruptures are a real and active area of research, but they operate at local and regional scales, not across 3,000 kilometers. These events are not talking to each other. There is a simple way to think about the energy involved. By the time the seismic waves from that far down Fiji earthquake traveled 3,000 kilometers to reach the seafloor off the South Island, they had spread out and faded to a faint tremor, a passing ripple, not a shove. To set off a fault, you need that fault already loaded to the breaking point, and then you need a real push. A faint ripple from across the ocean is not a push. The Puisagur segment ruptured yesterday because it was being squeezed by the Australian and Pacific plates the same way it has been squeezed for millions of years, not because a quake near Fiji reached out and pulled the trigger. And honestly, that grounded answer is more sobering than the conspiracy, not less. New Zealand's danger was never that some far-off quake would reach across the ocean and pull the trigger. The danger is sitting quietly right underneath the country the entire time, the overdue Alpine Fault and the locked Hikurangi megathrust, and it does not need a single earthquake near Tonga to be real. The activity at both ends of the boundary this week did not create New Zealand's risk. It just reminded everyone that the risk is always there. So where does that leave us? In the short term, watch the southern segment for aftershocks. Expect more magnitude 4 and 5 events out near the Auckland Islands over the coming days. That is normal, and given how remote it is not a threat to anyone. Seismologists will also be watching whether activity along the boundary keeps shifting closer to New Zealand's populated regions, because after the Tonga quake earlier this year, some of the aftershock activity did appear to migrate down toward the Kermadec end of the trench in New Zealand's direction. But the headline takeaway is this: New Zealand is not in danger from yesterday's magnitude 6. That was a routine, shallow, well-behaved earthquake on a remote stretch of fault that has seen far bigger. The real story is the one this quake points to. New Zealand lives on one of the most energetic plate boundaries on Earth, a boundary that flips polarity through the country, fires at both ends in the same week as a matter of routine, and carries an Alpine Fault that is now past its 300-year clock, with a 75% chance of a major rupture in the next 50 years. That is why every quake on this boundary gets watched, and why this one was worth a closer look. New Zealand has to stay on alert, not because of 1 magnitude 6 off its southern coast, but because the fault that matters is the one running right under its feet, and it is overdue. We will be tracking this as it develops.